Okay, so welcome back to the next in our little series looking at your entropy notes. So what you'll need to do is look at pages 19 and 20, and you'll need to go onto YouTube and find some video clips on barium hydroxide reactions and fill in those 2 pages. When you've done that, we're going to be looking at the top of page 21. And we're looking at why chemical reactions don't appear to happen even when we've calculated that we've got a positive delta S total. So we're on the top of page 21 and we're looking at calculating the delta S total of the reaction of methane being burnt in oxygen to form carbon dioxide and water. And we've calculated here our delta S system term, and that comes out as a negative number. Then that's what we'd expect because we're going from 3 moles of gas here to 1 mole of gas here. So we're expecting that to be a negative number. But this is a very exothermic reaction. So we get a very large positive delta S surroundings. So when I add those 2 numbers together, you'll see that my very large positive surroundings dwarfs the negative system, and we come out with a very large positive number. But we also know from experience that methane and oxygen do not react spontaneously together, or at least not at room temperature and pressure. Now, does this mean we've somehow broken the second law? Well, of course not, because nothing breaks the second law. But this delta S total value here, it only tells me that the reaction is spontaneous. In other words, it goes at room temperature and pressure. But it doesn't tell me how fast it goes. And that's the problem. This reaction is spontaneous at room temperature and pressure, it's just incredibly slow. The reason for that is because the activation energy is too high. And because the activation energy is too high, the reaction is too slow to be observed at room temperature and pressure. Obviously, if I was to come along with a match or something like that and light this mixture, it would spontaneously react, spontaneously explode more likely. But the reason for that is I've given it enough energy to overcome the activation energy, and once it gets going, because this is an exothermic reaction, it will rapidly go to completion. So my activation energy, which I'm defining at the bottom of this page, is the energy required for that reaction to occur. And we've got there a little enthalpy level diagram. So there's my methane and my oxygen reacting to form carbon dioxide and water. And I've got a very large activation energy. So very few particles have enough energy to overcome it. Most of them just fall back this side. But if I was to light a match, I would give enough of them enough energy to overcome that activation energy, and I would get this reaction occurring. So we're looking at the top of the next page, and we're looking at thermodynamic stability and kinetic inertness. So I've got 2 reactions here. I've got an exothermic reaction where we say the products are more thermically stable than the reactants. The reason for that is they are lower down on this enthalpy level diagram. So this is my enthalpy at the side. And the progress of the reaction is my reactants are going and turning into my products. On this side, I've got an endothermic reaction, and here I say that the products are less thermically stable than the reactants because they're higher up. So this one is said to be thermodynamically unstable. So we've got those 2 things, thermodynamic stability and kinetic stability. So that finishes this section of the notes. And it helps us to answer one very important question. Why do chemical reactions happen? And the answer is very simple. Chemical reactions happen because the delta S total is positive. That is, in a nutshell, the second law of thermodynamics. For any spontaneous reaction in a closed system, the total entropy must increase. But note it doesn't say anything about the speed of the reaction. Only that the reaction is feasible. In other words, it goes at room temperature and pressure. In the next section of the notes, we're going to look at Gibbs energy, and that'll be the final video in this entropy series. I hope you found them useful. Take care, and goodbye for now.